Welcome to this NPTEL course on Advanced Prestressed Concrete Design. In the last week, we discussed about the need for prestressing. In this part of the first week module, we will discuss about what are the different types of prestressing, what are the various systems that are available, and then various devices that are used for prestressing. And the expected learning outcomes after the student goes through this module will be he or she should be able to explain the different types of prestressing and explain the procedure of pre as well as post tensioning and discuss various equipment that are used in post tensioning and pre tensioning process, and also should be able to compare the differences and advantages between the two prestressing methods. Now, the types of prestressing can be classified depending upon what is the source of prestressing force. So, what is the meaning of source of prestressing force? I can create the prestressing either through hydraulic prestressing, which is the most common method of prestressing, and we all know that liquids are incompressible. When you try to compress through some means, it generates a lot of reaction force. Using this principle, we can apply huge amount of force. So, that is the basic principle of hydraulic prestressing. We can also apply prestressing by mechanical means. Somehow, if I am able to stretch by some mechanical anchorages and then release it, that also can induce prestress to concrete. And the third form of prestressing, which is the electrical prestressing, as you all know, metals are conductive in nature. When you pass the current, they tend to heat up, and then due to heat up, they actually elongate. So, through that means also, we can elongate the strand and then apply prestressing. So, this is an electrical prestressing. And the fourth way is, it was very popular in erstwhile USSR, where they used expansive cement and then created tension in the prestressing strand. In this way also, we can apply tension to the prestressing steel, thereby the tension will get transferred to concrete in the form of compression. So, this is one classification of how do we go ahead and talk about different types of prestressing based on the source of prestressing. We can also classify depending upon whether you tension the steel before you pour concrete or after pour concrete. That is a pre-tensioning or post-tensioning, which we will discuss in detail in the coming slides. We also have whether if the prestressing steel is within the cross section or outside the cross section, depending upon the location of the prestressing steel, we can classify the prestressing as external prestressing or internal prestressing. Now, depending upon the profile of the strand, again if it is a linear profile or a parabolic profile, or if it is going to be circular, depending upon what type of structural element that we do, we can classify the prestressing as a linear prestressing or a circular prestressing, predominantly based on the profile of the strand that we use. Another common classification is we can classify the prestressing as full, limited or partial prestressing depending upon the amount of tension stress allowed. When I say full prestressing, under service loads, you are not supposed to have any tension. In a limited prestressing, you can have tension stress, but the tension stress cannot exceed the cracking strength of the concrete. In partial prestressing, again tension stresses are allowed, but again there will be limits on the amount of tension that is allowed. So, that is basically depending upon the amount of tension stress that I am allowing in the concrete. Finally, depending upon how many directions that we are doing prestressing, we can classify them as uniaxial, biaxial, multiaxial prestressing, depending upon the direction of the strands that are used for prestressing. These are some of the ways with which we classify the types of prestressing. This we have already discussed, and hydraulic prestressing is the most common form of prestressing, where we use hydraulic jacks and oils to apply the prestressing. Now, what happens to the length of the beam while you do the prestressing process? For example, this here we have taken a small example where I am taking the original length of the steel as this, which is L1, okay, and typically the L1, because I am going to stretch and the prestressing steel is going to really behave like an elastic rubber band. When you stretch it, it is going to stretch quite a bit, and so it is usually taken as less than the length of the beam itself, I mean before applying the prestress, right? And then when you stretch it, obviously the length of the prestressing steel becomes more, and L3 is the while you transfer the prestress, then what happens is the length of the beam L2 becomes L3, which is going to be shorter than the original length of the beam itself, because when you transfer the prestress, the beam also undergoes some deformation, it undergoes shortening. Because of that, the length of the beam will become L3, which will be less than L2. Now, finally, while the beam is under service and then the concrete undergoes losses and steel also undergoes losses, there will be loss in prestress. So, finally, the beam will settle at a length which is a final length of the beam L4, which will be between L2 and L3. So, one thing that you have to note here is the prestressing steel actually stretches like your elastic rubber band, and if, especially in a post-tension system, if the length of the prestressing cable is quite a bit, you can get stretching in the order of 400-500 millimeter as well. So, really steel here behaves like an elastic rubber band. You have to keep that in mind. So, that is the stretching that helps us to transfer the amount of compression to the concrete. Now, we will move on to what is the difference between pre-tensioning and post-tensioning. This is a schematic that explains what is pre-tensioning method. As the name indicates, in pre-tensioning, you tension the strands even before concrete is poured. We will show some examples of how this process is done in the later stage. First stage is where the tendons and reinforcement are positioned in the beam mold. That is what it is shown in the schematics as well. You keep a beam mold. Before pouring concrete, you keep the tendons and reinforcements. Then the next stage is the tendons are stressed. Usually the tendons are stressed to 70 or 75% of their ultimate strength. So, that is what it is. They are stressed in stage 2, and the stage 3, after the tendons are tensioned to the required level, the concrete is cast into the beam mold and they are allowed to cure to the required initial strength. Concrete is allowed to cure for at least minimum period, so that when you transfer the prestress, it should not exceed its compressive strength than the allowable value. Also, when you transfer the prestress, you also have lateral tension that is developing in the anchorage zones. So, that also we need to make sure that the concrete is sufficiently strong enough to tackle all these stresses. In the stage 4, once the concrete is cured, the stressing force is released. In pre-tensioning, typically what we do is we cut the strand or tendons, and while we cut it, the pre-stressing force is getting transferred, and the tendons are going to anchor themselves in the concrete. Here it is a bonded system. It is a bonded system. It's a bonded system. And pre-tensioning is actually used for making precast components. Precast components are typically made using pre-tensioning method. So, this is the steps that are involved in pre-tensioning. Now, this is again this is a very nice technique for mass producing precast elements. This is also sometimes people say that as a long line method of production. Long line method of production. So why do they call that as long line method of production? Is in fact it was invented by German engineer Heuer. So it is also called as Heuer's long line method of production. The process is same as explained in the previous slide. You have mold and then you have prestressing strand that is stretched and kept ready and concrete is poured. Now this length of this pre-tensioning bed can be quite long. I can produce elements of certain length, multiple numbers. Okay, so this is what you have here, the pre-tensioning bed. Usually you have these end abutments where the tendons are anchored, and then you have stressing bed. This is also a very stiff abutment where you pull the strand like this using a hydraulic jack to the required amount of prestressing, and you can make elements of whatever the length that you want, and then you can also have in between formworks that are attached with holes where the tendon can go through. Then we can also have some removable abutment depending upon the type of element that we are casting, right. So once the tendons are detensioned, so what are the detensioning processes? Once all the concrete is poured and concrete is going to bond with the already tensioned steel. Now when I cut this strand like this, okay, for example here if I try to cut the strand, so basically the prestress will get transferred. So it is going to apply compression to the concrete and the concrete is undergo some shortening. So that's why you have this delta which is called as elastic shortening. So because of the applied compression, the beam is going to deform in compression. That is called elastic shortening. So the overall length of the produced element will become L minus delta, which is your elastic shortening. Now this is the system that typically used, it is a very common used system, which is assembly of a prestressing strand. So this is a strand, and usually the strands are 7-wire strand, and you have this kind of a wedge system. It's a wedge. It's usually 3-piece wedge. They are connected together by this ring, retaining ring, and then this 3-system wedge that goes through this body, anchorage body, okay, and the anchorage body also will have a tapering size. And one thing to note here is while you do the tensioning, the wedges will go and sit against this block, the body that it is written here, and through wedge action it will transfer the prestress. In fact, the wedge cannot come out, it can go only inside and it cannot come out like this. So while you stretch it, the wedges will go inside and then it will sit, and through the process of friction and wedge action, it will grab onto the strand and it will not let it to go back to its position quickly, right. So in this way you lock the strain in a pre-tensioning system. So you also have a cap which you close the wedge system within this anchorage block. Now this is a picture of a precast plant where pre-tensioning bed is shown. You can see here you have pre-tension steel is there at the top as well as at the bottom. So you have both locations, you have pre-tensioned steel is there, and this is called as, this system is called as bulk head, okay, and this, the entire system is called as anchoring head, okay, and this is the anchoring head is where you apply the prestressing, and that helps in the transfer of the prestress as well. And bulkhead is actually helping you to hold the strands at a particular location depending upon the design what you have, and also it will act as a formwork for connecting the beam mold so that you can pour concrete within them. And this bulkhead also typically it sits and it is actually it can move. For example, you see here this is sitting on a roller and this is some kind of a rail. So this can move along the length of the bed depending upon where you want to stop this particular bulkhead, depending upon the length of the element what you produce. So this is the system. The design of this bulkhead and anchoring head itself is a challenging one, and you have to design it properly so that it is able to perform the way you want it to be. Okay, this is an example of a cage, pre-tensioned beam cage reinforcement. You see plenty of reinforcement that you see here. You see all these vertical stirrups that are going there, and you also what you see here is a pre-stress cable that is going like this straight, and it is all coming like this, right? You have a linearly varying cable, okay, with the one slope here, and there is a constant, it is flat here, and it is going like this. At the mid-span location, you see here all the strands are at the bottommost location. The reason is you want to generate more eccentricity for this pre-stressing strand. Then only I will develop more pre-stressing moment that will help me to offset the loading that is coming from external load. Then while we come towards this anchorage zone or the bulkhead location, the strands will get splayed. The reason is we want to reduce the stresses at the bulkhead locations so that you are not going to have any failure when you cut the strand. So typically these strands will get splayed as you move towards the support locations, so that while you transfer the pre-stress and while you do the stretching, you don't have any problem of premature failure. Now you can ask me how this particular cable profile is being maintained. So you have to keep this cable at a particular eccentricity along the length of the beam, that we have to do it carefully using something called deviators. So you have to push this cable to be there at a particular location, so that once you pour the concrete and then when you cut it, they still remain at the same location and then help you to create that uplift force that what you want, right? So this is one example of reinforcement cage that is ready for form closure and pouring for a pre-tensioned beam. And this is the example how you do the harping, okay? Typically at the bottom of the mold, you will also have some anchoring points, which we will see in the next slide. So you push through this vertical jacks, the cable, so that they are kept at that particular location. For example, you see this is again a vertical cable that is helping you to push this pre-tensioning cable at a particular eccentricity. So you see here, this is the way it is. Now you have an anchor here, right? So these anchorages are pushing it down. So I am applying actually a vertical pre-stress to the cable itself. Now how is this particular cable will be anchored? Below the bottom bed of the formwork, you will also have some anchoring points, and after the pre-stressing is applied, you can see here the eccentricity is going like this. This is at the mid-span location, is going like this. So this location is a mid-span location where I want maximum eccentricity, right? So that's what we want. So this is the way that we try to keep this cable profile at a particular eccentricity by employing vertical pre-stressing. Okay, this is the way it is held. For example, this is the deviator, which is that I told you that cables are being pushed by vertical, but then I have to hold it. So there is a rail at the bottom of the bottom below the bottom formwork. That vertical cable will be anchored to that rail, and in that way I can apply the vertical pre-stress how much I want, right? So in this way I can maintain the cable profile to the eccentricity level that what the designer wants. Now, so this is briefly about pre-tensioning method. Now, in pre-tensioning also, sometimes mostly they are bonded system. They are always bonded system because through bond with concrete only the pre-stress gets transferred. But sometimes at the anchorage zones, if you want to avoid premature failure or avoid cracking, some of the pre-stressing strands will be unbonded by having some kind of a splice. So that means the contact between concrete and pre-stressing steel for some of the strands will be purposefully kept not in contact by providing some kind of a sleeve to reduce the amount of force that is coming at the bulkhead locations, right. So, in this way we can create an unbonded system for some elements even in a pre-tension system depending upon your design requirements. Now, we will move on to the post-tensioning. Again in post-tensioning, as the name says, here you are tensioning the steel after the concrete is poured. Okay. Here you have multiple varieties again, multiple types are there. You have internal post-tensioning, then you have external post-tensioning. Now, what is internal and external? When I say internal post-tensioning, the strands are always located within the cross section, within the concrete. When I say external, the PT cable may be outside the cross section or within the cross section, but they will not be in contact with the wall, contact with the concrete. Okay. So, that is why I said if it is not sitting along with concrete, it is called external. Okay. And in internal also, now we have two systems, bonded and unbonded system. In pre-tensioning always they are bonded system, but in post-tensioning depending upon whether you grout the duct, it can be a bonded system or unbonded system. But in external post-tension system, they are invariably unbonded system. Okay. Now, what do we do in post-tensioning? We first place the reinforcing cage and post-tensioning ducts inside the formwork, right, and then we do the casting and curing of the concrete. See, now please note that we have not tensioned the steel yet, already we have poured the concrete, but the tendons and duct through which the tendons go through are already in place. Now, after concrete is cured, then you go ahead and tension the tendons and then they are anchored with special jacks that react against the member. This is the key. In pre-tension system, you need separate anchoring system for keeping the pre-tension cable or steel, prestressing steel in tension. In this case, you see here, you are applying jacks and you are reacting against the concrete element itself to generate the amount of pre-stressing that you want. So, it is a self-reacting system. So, you are applying tensioning by reacting against the member itself. Okay. So, this is the way the difference between a post-tension system and a pre-tension system. Unless you are using unbonded tendons, typically the duct will be there, which I will show you in the figures in the next slides. The duct will be grouted to complete the post-tensioning operation. So, what is the meaning of grouting? So, you have a duct and you have run the cable. Now, you are stretching the cable. Now, everything is getting locked, right? And the pre-tension, the tension that you apply on the strand will get transferred in the form of compression to the concrete. But then you have to close the gap between the duct and the pre-stressing steel by applying grouting. If you do not do the grouting, it becomes an unbonded system. If you do the grouting, it becomes a bonded system because the steel is now bonded through grout with the surrounding concrete. So, we will discuss what are the advantages of bonded and unbonded system in the coming slides. But if you do not grout it, if there is no physical contact between the steel and the surrounding duct, then it is an unbonded system. But if you grout it and there is a physical contact between the pre-stressing steel and the duct through grout, then it is called a bonded system.